All right, welcome back. So we want to look at this example here with the root test. And the root test is, again, designed really to work well when you're dealing with exponents that actually involve the variable that you're indexing on. So this is my index variable, so when I eventually set up the root test, it'll be limit of the kth root of this stuff. And the root test, it really works well when you have stuff being raised to expressions involving k. As k is your index variable. Now, before we do that, before we actually apply the root test, let's just examine this sequence a little bit, or this series a little bit. So if we were just looking at the series that involved just the stuff inside, no exponents, it was just a series of k over k plus 1, then we could quickly say to ourselves, this thing will diverge. If we were just looking at the stuff inside, because we know that the limit of the stuff inside goes to 1. Right? We know the limit of the stuff inside goes to 1. And so therefore, since the stuff inside goes to 1, right, we know that it would diverge, right, by the divergence test. Right, so if we're just looking at that stuff inside, we would only, without the exponents outside of it, we would definitely say that it diverges. But now that stuff's being raised to a power. Now the important thing to realize is that as this thing does go to 1, it's always smaller than 1 though. Right? K is always smaller than k plus 1 by just a little bit. So this stuff is always smaller than 1. Well, when you take numbers smaller than 1 and raise them to bigger and bigger powers, that stuff is going to go to 0. Okay, that stuff is going to go to 0. The question becomes, does it get to 0 quick enough so that we actually converge, or does it not, in which case we diverge? And that's what our root test is actually going to tell us as we start to work this out now. Okay. So the root test, we say rho is the limit as k goes to infinity of the kth root of all that stuff. K over k plus 1 raised to the 2k squared. Now to simplify that, remember that when we take the root of something, that's the same as raising it to the 1 over k power. So the kth root of this stuff is the same as the stuff inside raised to the 1 over k power. But remember, when you take something with an exponent and raise it to a power, you multiply the exponents. So we're going to have 2k squared times 1 over k. That means this will simplify to be k over k plus 1, now raised to the 2k power. So we're faced with taking this limit now. Well, as we try to take this limit, we quickly realize as k goes to infinity, k over k plus 1 is going to go to 1. So that's a 1 inside. As k goes to infinity, the exponent's going to go to infinity. So we're dealing with a 1 to the infinity limit, which again is one of our indeterminate forms. So for that reason, we need to apply the logarithm. Take the limit first. Okay, so we do that. Limit as k goes to infinity. If we applied ln here, we'd have ln of that stuff, so the 2k would actually come out front. And then we'd have ln of k over k plus 1. Okay, and so, as always happens when we apply the ln to one of these exponential indeterminate forms, it always transforms into an infinity times 0 or 0 times infinity, either one, limit. And that's what happens here. Because as k goes to infinity, 2k goes to infinity. As k goes to infinity, k over k plus 1 goes to 1, and ln of 1 is 0. So this is the indeterminate form, infinity times 0. Remember to handle infinity times 0. We take one of the things, divide it by the other. Take one of the things, divide it by the other. So course, it makes the most sense to put the ln on top, divided by the reciprocal of the other. I don't know what I just said a minute ago. I think I might have misspoke. Ln of k plus 1 over the reciprocal of the other. So that would be 1 over 2k. And so finally now we have transformed this into, in this case, a 0 over 0 limit. So we can now apply L'Hopital's rule and take the derivative. Now, we could take the derivative of ln of k plus 1 as it is right now. Right? Take the derivative of ln of k over k plus 1 right now. Right? That would be 1 over that stuff times the derivative of that stuff, which would require the quotient rule. Or I can step aside here for a second and say, hey, remember that when I do the derivative of the ln of something, instead of doing the normal roll here, let's remember that I can write that as ln of k minus ln of k plus 1. Right. So rather than having to do 1 over that stuff times the derivative using the quotient rule, I can just do it this way. Right? And that's what I'm going to do here. Take my derivative. So that would be 1 over k minus 1 over k plus 1. Okay. So that's what we're doing now. We're applying L'Hopital's rule. So back to my original problem now. Limit as k goes to infinity of 1 over k minus 1 over k plus 1. It's the derivative of the top over the derivative of the bottom. 1 over 2k. But 1 over 2k is just 1/2 of k to the minus 1. So do the derivative. That would be minus 1 times the 1/2 times k to the negative second, or minus 1 over 2k squared. Okay, so all we need to do now is simplify this thing and see what happens to it. Simplify this thing here and let's just see what happens. So, towards that end, I recognize up here that I have a messy fraction over another fraction. Now you could do your fraction arithmetic, just add those fractions and get a common denominator. And that works. Or what I'm going to actually do is what I typically do when I deal with a complex fraction, and that is multiply both top and bottom by my common denominator for all of the little fractions. So k plus 1, 2k squared. So I'm going to need a 2 to go with the 2k squared. I have a k and a k squared, so I'm going to need a k squared. And we have a k plus 1 factor. Right? And we're going to multiply both top and bottom by that expression. Okay? And then simplify. So in the first fraction there, we will have limit as k goes to infinity. 2k squared will cancel with the k to give me a 2 times k plus 1. Actually 2k k plus 1. Still have another k left over. 2k k plus 1. And then when I get to the second one there, the k plus 1 is going to cancel out. The k plus 1 is going to cancel out. Right? And I'm just going to have minus 2k squared. Okay, and then in the bottom, the 2k squared cancels out with the 2k squared. So I have a minus 1 times k plus 1. Okay. And now we go through and we do a little bit of simplifying. All right, 2k squared times k is going to be 2k squared, which will cancel with the other 2k squared. And then we'll just have 2k times 1 on top. So limit as k goes to infinity of 2k on the top over minus k minus 1. And now finally, we have transformed this thing after a lot of work into a limit that we can now just realize the k's are going to cancel out. And so I'm going to have 2 over minus 1. And the 1 down there doesn't matter, right? Because we're going to infinity. So this is just going to be minus 2. So the limit of the ln of the sequence approaches minus 2. So now that takes us back to our limit. All right, that takes us back to our limit now. Rho, which was the limit as k goes to infinity of that stuff to the 2k. We know now that that is going to be equal to e to that limit. That equals e to the minus second. What is e to the minus second? Well, that's going to be 1 over e squared, which is going to be roughly the decimal point 135 and so on. But what is important is that that number is less than 1. That number is less than 1. And so therefore, we know that our original series will converge. Okay, so it turns out having that expression, even though the limit inside will be approaching 1, raising it to the 2k squared is enough. Raising it to the 2k squared is enough so that we can say with confidence then that, yeah, it is actually going to be enough to make it small enough so that it will actually converge. The infinite series will actually converge.